Hi students, welcome to this video session. My name is Samuel Emeka, as usual. In this video session, we shall discuss the fundamental counting principle. This will be the first part of the video, so we shall have other parts where we shall solve more questions. This video is the first in the playlist on counting and counting techniques. It's going to be a playlist on counting and counting techniques, and this is the first video on it. So in this video we shall determine the number of ways we can accomplish two tasks in succession or consecutively. Consecutively means one task after the other, like after we accomplish the first task, then we move over to the second task. We shall also determine the number of ways we can do multiple tasks in succession or consecutively or successively. It means the same thing, whether we say consecutively or successively or in succession, it means the same thing. So the fundamental counting principle is also referred to as the fundamental principle of counting. In some textbooks, you will see it as fundamental principle of counting, or the multiplication principle, or the counting principle, or the principle of counting. These are the other names by which you can also refer the fundamental counting principle. Now, I sing and dance, so let's see what will happen here. I sing tenure. Abide with me, fast falls the eventide. I sing bass. Abide with me, fast falls the eventide. So you see, you will rate me the best singer, right? I hope you rate me the best singer. Then let's come to dance. I dance the Igbo traditional dance. You know, you can see me here dance, and I don't know how to display it here. How many of you would like to see me dance? Raise your hands. Then I dance reggae dance, and I also dance disco dance. So let's look at this now. How many ways can I sing and dance? When we talk of the fundamental counting principle, we wanna count, or we wanna determine how many ways we can do stuff. You know, how many ways we can accomplish tasks in succession. That is the idea of the fundamental principle of counting, or fundamental counting principle. So let's look at this now. For instance, I sing tenor, I sing bass. So this I can do in two ways. I can do this in two ways. Then I dance Igbo traditional dance, I dance reggae dance, and I dance disco dance. So this I can do in three ways. In three ways. So if you're asked how many ways can I do these two tasks, I can sing two ways times. I can also dance three ways. Now, assuming we have to represent this, let's see if we can represent this, okay? So that we can kind of say it. Let's write the singing here. Sing. I sing tenor. Let me say tenor is T, and let me say bass is B. Then dance. Dance. let me say in dancing that Igbo traditional dance is I. Let me call this I. Then reggae dance is R. Then disco dance is D. Now, because I have to do it for each one, okay? Here I have the Igbo dance as I, uppercase I, reggae dance as uppercase R, and disco dance as D, uppercase D. So if you look at this, I can sing tenor and also dance Igbo dance. So that will be T-I, not the singer, okay? Now, the next one is I can sing tenor and dance reggae dance, that is T-R. I can sing tenor and dance disco dance, and that will be T-D. I can sing bass. I can sing bass on dance and dance Igbo dance, that is B-I. You know, I just talk tenor, but I can also talk bass. I can sing bass and dance reggae dance, and that will be B-R. I can also sing bass and dance disco dance, and that would be B-D. So if you look at the number of ways I could do this, how many ways do you see here? 6 ways. So, you know, you can just say we can sing, I can sing 2 ways or two voices, and I can also dance 3 types of dance. So it's just 2 times 3, which is 6 ways. So in this video, we shall look at the how many ways we can accomplish tasks. Okay, we shall look at how many ways we can accomplish tasks. Okay, so I've listed it and it's 6. 1, 2, 3, 4, 5, 6. Or you can just say 2 times 3, which is 6. Okay. So what does the fundamental counting principle say? It states that if a task can be done in A ways, just like I can sing in 2 ways, and another task can be done in B ways, just like I can dance in 3 ways, then the total number of ways of doing both tasks consecutively, like I said, consecutively means successively or in succession, will be A times B ways, just like we have 2 times 3 ways, which is 6 ways. So that is what the fundamental counting principle is all about. Now, what if we have to do multiple tasks, like more than 2 tasks, right? So that leads us to what we call the generalized multiplication principle. And it works with this, you know, if you can do one task in A ways, you can do another task in B ways, you can do another task in C ways, you can do another task in D ways. Then the total number of ways of doing those tasks in succession is A times B times C times D. Okay? No matter how many tasks you have, the total number of ways of doing those tasks will be the product of the number of ways of doing each individual task. Okay? Do you get it? All right. Now let's start solving problems, okay? Mr. C has 2 shirts, a black shirt and a white shirt. He has 3 pants, a black pant, a red pant, and a green pant. In how many ways can he dress up for work using any combination of shirt and pant? And this looks just like what we did here. And for your information, this is called a tree diagram. Looks like a tree, okay? Looks like a tree. This topic is related to probability. So after this, we do permutation, we do combination, then we do probability. So this example 1 is just equivalent to what we just did. Assuming I have a black shirt Let me call this BS. And I have a Y shirt. Let me call this WS. 3 pants, a black pant. Let me call this BP. Then red pant. Let me call this RP. And then green pant. So how many ways how many combinations of a shirt and pants can I wear? So you see, if we have a shirt, and then we have a in shirt we can have the black shirt or the white shirt. Okay, and then pants. My pants could be a black pant. It could also be red pant. You know, for each shirt I could wear that red pant, or it could also be green pant. Okay. For the white shirt, I can also wear a black pant. I can also wear a red pant. And I can also wear a green pant. So the combination of what I have for shirt and a pant will be this. Looks like a tree diagram. So it could be BSBP, black shirt, black pant. It could also be black shirt, red pant. It could also be black shirt, green pant. Okay, I can I can also wear a white shirt with black pant. I can also wear a white shirt with red pant. I can also wear a white shirt with green pant. So 6 ways. How many ways can I can wear any of these. So 6 ways. Or you can just say 2 times 3. Okay. For the shirt is 2 times pants is 3. Okay. 2 times 3. Let me use this. And let me kind of erase this eraser for this. So 2 times 3. And that will give us 6 ways. 6 ways. Okay. All right. Next question. Zine Dinners offers 12 main courses, 5 desserts, and 7 sides. How many ways can a person order a 3-course meal? So the person can order either any of the 12 main courses, 5 desserts, and 7 sides. So the 3-course meal will comprise a main course, dessert, and sides. So the number of ways will be 12 times 5 times 7. Okay. First task can be accomplished in 12 ways. Second task can be accomplished in 5 ways, and third task can be accomplished in 7 ways. Or 12 courses, 5 desserts, 7 sides. So 12 times 5 is 60, times 7 is 420. 420 3-course meals. 420 3-course meals. All right. So do you get it? Example 3, Social Security. The U.S. Social Security number contains 9 digits. How many different Social Security numbers are possible if A, repetition of digits is allowed, B, repetition of digits is not allowed. C, the first number cannot begin with 0 or the first digit. Okay, now let's kind of visualize this for a moment. If let's start with the A. Now let's visualize this. Let's draw 1, 2, 3, 4, 5, 6, 7, 8, 9. Let our D be digits. Okay, so it has 9 digits or 9 numbers. D, 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 D. So if repetition of digits is allowed, how many digits do we have? 0 to 9. So we have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If you count it, okay, it's 10. So we have 10. So, and repetition is allowed. So first one could be any 10. Second one could be any 10, 10 ways. Third one could be any 10, 10 ways. Fourth one could be any 10. Fifth one, any 10. Sixth one, any 10. Seventh one, any 10 digits. Eighth one, any 10. Ninth one, any 10. So any of the 10 digits could be the first one. Any of the 10 digits could be the second one. Any of the 10 digits could fill the third spot. Any of the 10 digits could fill the fourth spot. Okay, so when you determine the number of ways, it is 10 raised to power 9 ways, or 1 billion ways. So 1 billion social security numbers. Now, have you ever thought of this? Okay, kind of thinking about, okay, when do you think we will run out of social security numbers? Is the United States population ever going to be up to 1 billion? Okay, so this is kind of one of the applications of counting and counting techniques. It helps you to plan. If you're managing a company, or if you want to build a startup or a firm or a company, your employee IDs, and you need to give your employees IDs. How would you name those IDs? Are you going to use only digits, or are you going to use letters and digits, like in license plates? Okay, or are you going to use only letters? Now, if you're using only digits, do you want to use 1, 2, 3? If you use 1, 2, 3, that means you only have like 9 people then. Okay, are you going to use 001, 002, 003? You know, like, so if you kind of with counting, it kind of tells you if you know how many numbers you can get, then you plan. When you're giving your employees ID, you want to plan well to accommodate. I mean, if your company is going to expand in the future, you don't want to run out of numbers. So if you look at the social security numbers, you know, the population of the United States now, which is less than 500 million. Yeah. So it's kind of, if you look at it, it's possible we probably wouldn't run out of social security numbers. If we are going to repeat digits, we could have a 1 billion social security numbers. Now, B, repetition of digits is not allowed. Now, what if we can't repeat digits? Then let's use the next slide and do it. So let's visualize this also. 1, 2, 3, 4, 5, 6, 7, 8, 9. We can repeat digits. Okay, so if this is 10, then this will be 9, then this will be 8, then this will be 7, this will be 6, this will be 5, this will be 4, this will be 3, and this will be 2. Because look at the way it's done. If you can't repeat digits, okay? Any of the 10 digits could fill the first one, and you can't repeat the digits. So only 9 digits remain. Any of the 9 could fill the second spot. You can't repeat digits. Any of the 8 could fill the third spot. Any of the 7, fourth spot. Any of the 6 digits remaining could fill the fifth spot. Any of the 5 could fill the sixth. Any of the 4 digits could fill the seventh. Any of the 3 digits could fill the eighth spot. And any of 2 digits could fill the ninth spot. So what you got here if you do this? Because of time, I'm going to use my calculator. 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2. And that will give us 3, 6, 2, and you can do this, okay, to confirm. 8, 8, 0, 0. Okay, 3,628,800,000. I mean, yeah, 3,628,800. Yeah, that will really be small, you know, if we cannot repeat digits. So, but if you look at it, of course, we repeat digits in the U.S. Social Security numbers. Okay, so that's what you will have if digits, if you cannot repeat, if a repetition is not allowed. Now C is this. C is that the first number cannot begin with 0. Now I'm not sure, but are there Social Security numbers that begin with 0? I'm not sure. Anyway, with this question, if they ask you this question and they don't tell you that repetition is not allowed, okay, any question they ask, if they don't tell you that the repetition is not allowed, then you have to do it as if repetition is allowed. Yeah, but this C, you have a condition that the first digit will not be 0. So let's visualize this 1, 2, 3, 4, 5, 6, 7, 8, 9. My 9 is kind of big. 9. So here we have our digits, digit, 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 digit. We know that the first number cannot be 0, so we have only 9 available in the first spot, right? And they didn't tell us that the repetition is not allowed. If they ask you the question like this, the first number cannot begin with 0, and they did not tell you that repetition is or is not allowed, you will assume that it is allowed. Okay, so you have 10 digits. 0 cannot be there, so you only have 9 digits that can fill this top first spot. Then the rest could be 10, 10, because the rest could be 10 in each spot, because you assume that repetition is allowed. Okay, so what you got when you do that? You have a 9, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So you have 900 million numbers. Example 4. The local 7-digit telephone numbers in Jacksonville, Alabama have 256 as the first 3 digits. How many different telephone numbers are possible in Jacksonville, Alabama? So let's kind of visualize this. It has 7 digits, right? The local one. So 1, 2, 3, 4, 5, 6, 7. And the first 3 digits we have 256. 256 as the first 3 digits. Okay. This is digit, 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 digit. So this already has been given to us. So there is only one way of doing this. Okay. There's only one way of putting these two. Only one way. 2 can only occupy this one time. 5, there's only one way of having this 5 in the second spot. 6, there's only one way of having it. Okay, among all the digits, the 256. So now, if you have this 4, and with the question they did not tell you that repetition is not allowed. If they did not say that repetition is not allowed, then you have to do it as if it's allowed. So this digit, any of the 10 digits can be here. Any of the 10 can be here. Any of the 10 can be here. And any of the 10 can fill this spot. Okay? Any of the 10 can fill this spot. So how many are possible now? You now have 1 times 1 times 1 times 10 times 10 times 10 times 10. And that will give you a 10 to the 4th power, which is 10,000. 10,000 numbers are possible. 10,000 numbers are possible. Comprende? Question 5. You are taking a multiple choice question test that has 5 questions and 4 answer choices. You must attempt all questions and select one choice for each question. How many ways can you answer the questions? All right, let's visualize this. It's always good to visualize your your questions so that you can know how many ways you can do that. So we have questions, and then we have answers, answer choices, answers. This is another experience, writing with a mouse. Can you imagine that? So we have 5 questions. Okay, let's say Q1, question 1. We have question 2. We have question 3. We have question 4. And then we have question 5. And each of these questions has 4 answer choices. Let's call this A, B, C, D. A, B, C, D. Okay, A, B, C, D. A, B, C, D. So the same thing here. The same thing here. A, B, C, D. Okay. Which is each of them has 4 answer choices. Each of them. A, B, C, D. A, B, C, D. A, B, C, D. A, B, C, D. Okay, so you see that you must answer one choice per question. So you can do this 4 ways. Times, you can answer this question 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 4 ways. You can select any of the answer choices. So what do you got, folks? 4 raised to power 5, right? 4 exponent 5. 4 times 4 times 4 times 4 times 4. And that is a 1024. 1024. Okay? 4 exponent 5. That's what you got. 1024. Ways. Okay? Comprenez-vous? All right. Example 6. The value of a stock may go up. It could go up. Or it could go down. Or it could remain constant. I want to make sure I underline it well. Assume you own 10 stocks. How many possibilities do you have? So this is like what we did, you know, previously here in example 5. This is kind of what we did here. You have a, let's say you own 10 stocks, okay? You have a stock 1, stock 2, let's say S1, S2, S3, stock 3, X4, stock 4, S5, your fifth stock, S6, stock 6, S7, stock 7, let's say it's Google, S8, let's say it's Apple, S9, let's say it's Disney World, S10, let's say it's Walmart. These folks didn't pay me for mentioning their names, okay? Okay. Now, you own 10 stocks, and each one, it could go, the value could go up, it could go down, it could go up, GU, go up, or it could go down. You know what? Let me use another, let me use something else for that. These stocks could go up, or it could come down, or it could remain constant, each of them. So you have 3 choices here, you see, you have 3 choices here, 3 times the same thing here, you have 3 here, times the same thing here, you have 3. It could go up, it could come down, or it could be constant. The same thing here, you have 3 choices. For the 4th stock, you have 3 choices. For the 5th stock, you have 3 choices. For the 6th, 3 choices. For the 7th, times 3 choices for the 8th, times 3 choices for the 9th, times 3 choices for the 10th. So you have 3 raised to power 10, right? So what is it? What is 3 raised to power 10? Let's write our answer here. 3 exponent 10. That gives us 59049. 59049. These are the possibilities. Okay? 59049 possibilities. All right. Example 7. In the original plan for area codes in 1945, the first digit could be any number from 2 through 9. The second digit was either 0 or 1. And the third digit could be any number except 0. How many different area codes are possible with this plan? So it's good to visualize it as usual. Let's have our area codes. Area codes, which is it's usually 3 digits. And this is a 1945 plan. So we have 1, 2, 3. And of course, with area codes, you kind of have it like this first. Okay, so first digit could be any number from 2 through 9. So let's count it. 2, 3, 4, 5, 6, 7, 8, 9. So it's gonna be 8. 8. Okay, this is D, D, D. Digits, digits, digits. So it's gonna be 8 because it's 2, 3, 4, 5, 6, 7, 8, 9. I'm counting it with my fingers now, and I counted 8. Now, second digit was either 0 or 1, so it's only 2. It's only 2 because it's 0 or 1. Okay, are you with me? It's gonna be only 2 because it's 0 or 1. Then the third digit could be any number except 0. Okay, so that means it's because with 0 is 10 digits, so without 0 is 9 digits. So we got now 8 times 2 times 9. 8 times 2 times 9. And with this plan now, how many area codes do we have? 8 times 2 times 9. We have a 144 area codes with this plan. Okay? Example 8. The new license plate of the state of Georgia has 3 letters followed by 5 numbers. So 3 letters followed by 5 numbers. Just like you see here, ABC 1, 2, 3, 4, 5. How many license plates of this kind are possible if A. Repetition of letters and numbers is allowed, B. Repetition of letters and numbers is not allowed, C. Repetition of letters is allowed, but the repetition of numbers is not allowed, D. Repetition of letters is not allowed, but the repetition of numbers is allowed. Okay, so, and that is another thing about the counting principle. It helps you to plan how many license plates you can produce. And some states have specialty license plates. If they want to know how many they can produce, this will help them to know that. Okay, so A is that repetition of both letters and numbers is allowed. So let's do this. Let's do it in the next slide here. So our A, and as usual, if you can kind of do this first on your own and then check. So I have 1, 2, 3 for the numbers, and then for the letters I mean, and then 5 numbers. 1, 2, 3, 4, 5. Right? So now, let me call these letters L, 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 L. For the letters D, for the numbers, digits, D, 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 D. Okay? So, if repetition is allowed, right? So, how many letters of the alphabet do we have? We have 26. So repetition is allowed. So 26, 26. For the numbers, it could be 10, 10, 10, 10, 10. So when we multiply it, folks, what we got, if we multiply it, 26 raised to power 3 times 10 raised to power 5. Just do it as you want, okay? But what I have here is 1, 7, 5, 7, 6, 1, 2, 3, 4, 5. 1, 7, 5, 7, 6, 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. Okay. So this is how many they could get. 1,757,600,000 license plates if they allow repetition of the license plates. The next one, let's form our our 8. Okay, letter, 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 digit, 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 digit. L, 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 D, 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 D. Repetition of letters and numbers is not allowed. So if we have to do this, 26 we could use any of the 26 letters in the first part. After that, that letter is not allowed, so any remaining 25 could go to the second spot. After that, repetition is not allowed, so 24 will be here. We stop for the letters. Then the digits, this will be 10, this will be 9, this will be 8, this will be 7, this will be 6. So what do you got? 26 times 25 times 24 times 10 times 9 times 8 times 7 times 6. And that gives us 4, 7, 1, 7, 4, 4, 0, 0, 0. Okay, this is what we got. 471,744,000. C part. Let's still do our visual stuff. Letter, letter, letter. Digit, 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 digit. L, 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 D, 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 D. So here, repetition of letters is allowed, but the repetition of numbers is not allowed. Okay, so we have 26 here, 26 here, 26 here, 10, 9, 8, 7, 6. So what do we have now? 26 raised to power 3 times 10 times 9 times 8 times 7 times 6. That will give me 5, 3, 1, 4, 9, 8, 2, 4, 0. 531 498 240. Okay, 531,498,240. And then the last question on this 8. Letter, 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 digit, 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 digit. So letter, 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 D, 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 D. Repetition of letters is not allowed, but the repetition of numbers is allowed. So we have 26 here, we have 25 here, we have 24 here, then we have 10, 10, 10, 10, 10. And that gives us what? 26 times 25 times 24 times 1, 1, 2, 3, 4, 5 times 100,000. Right? 1, 2, 3, 4, 5. Okay. So that gives us 1, 5, 6, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I just want to make sure I didn't make mistakes. So 1, 2, 3, 4, 5, 6, 7. Kind of do something here. Okay. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, so what I have, folks, I have this 1,560,000,000. Yeah. If repetition of letters is not allowed, but the repetition of numbers is allowed. Example 9. CMAT Stores has a new store in 2 Egg, Florida. You know there's a place called 2 Egg, Florida. One of the employees has to paint the parking spaces with a letter of the alphabet and a single digit from 1 to 9. The first parking space is A1, and the last parking space is Z9. So, like when you build a new store and you have to kind of, when you want to park your car, some of the parking spaces are marked already. How many parking spaces can be painted with distinct labels? So, looks like we have a, let's visualize this. So, we have letter and digit. So, we have letter, digit. Any of the letters of the alphabet, so 26 will be here, times the digits is from 1 to 9, so let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's only 9. It's no longer 10. It's only 9. So 26 times 9 is what? 26 times 9 is 234. 234 parking spaces. 234. You can paint the parking spaces with 234 distinct labels. 234 labels. Okay. Example 10. How many different 5-letter radio station call letters can be formed if the first letter must be S or C? So we are looking at 5 letters. It's going to be 5 letters. Let's mark it. 1, 2, 3, 4, 5. L, 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 L. Now, remember the area code we did, the 7-digit code we did for Jacksonville, whereby it must be 256, and there's only one way for each one. But here, the first letter must be S or C. So S or C is the first letter. So that's 2 ways. Okay? And because they did not tell us, they didn't tell us that it could not be repeated. Okay, they did not tell us that it could not be repeated. Remember, if they had told us that it could not, it must not be repeated, then that's fine. Then that means we will know what to put. But since they didn't tell us that, any of the letters, we could have a 26 still here. 26, 26, 26. So, okay. So, here we now have 26 raised to power 4 times 2. So that is 9, 1, 3, 9, 5, 2. We shall do more problems because there are so many problems related to this. So other parts of the video would have varieties of questions, okay? And these are the references. Thank you so much for listening, students, and you have a great